Start a little early. What's that? Yes, it's kind of a weird caffeine. I don't know if that's accurate, but it's close. Yeah, it's meant to be caffeine. He's smiling with this little coffee. And this one's fun too because many people misspell angle and spell angel. And so the bond angel is 120 degrees. Okay, so we're going to jump into 9B. So this will do Wednesday. And we're going to talk about predicting bond angles in small organic molecules. So we're going to be looking at a lot of organic molecules today and just getting practice drawing Lewis dot structures of bigger molecules. Then on Wednesday and Friday, we're going to go back to sort of one, central atom with things around it, and looking at Vesper shapes and bond angles and why, like how we think that comes about in terms of the S and P orbitals. So a lot of sort of 3D thinking on Wednesday and on Friday, and then I will review that material when I come back on Monday. Yeah, so when I get back here next Monday, we'll review the stuff that we did on Wednesday and Friday. In case you have questions, then you'll have a chance to ask them when I get back. Okay. So for this valence shell electron pair repulsion theory and models, it helps us make larger molecules. So we're going to make some larger molecules today. We just kind of walk through the molecule and treat each new atom as a new central atom. So we've already made a lot of molecules, Lewis dot structures, like BrCl3 and all of these different things. But it was like one central atom and a bunch of atoms around it. Now we're just going to walk through the molecule, and most of the organic molecules are carbons bonded to carbons. And so we'll make a carbon backbone, and then we'll stick things on there. But we treat each new atom as a new central atom, count those electron domains, and we'll determine what their shape is. Okay. So we'll draw that structure around that atom and move to the next one. So we use this handy table to name the structures and determine the bond angles around the central atom. And so that's this big deal. You need to learn what those wedged and dashed bonds mean. And so we'll talk about those a lot today. But all of these little wedges and dashes, that's meant to give you an idea of the 3D shape of it. Okay. So we're showing these wedges as coming out of the board and the dashes is going into the board. So that's what they're trying to convey with those. So let's draw some molecules. So we'll start with the easy one. This is methane. And so like we've done before, you can draw it all flat if you just want to draw the Lewis dot structure for this. So carbon likes to bond with 4 things, and hydrogens can only bond with 1, and so we're done. We come in with 4 valence electrons on the carbon. We have 4 more for the 4 hydrogens. So we have 8, and we've used them all up, 2, 4, 6, 8. Now what we would like to do, though, is use this. This is 4 domains, 4 electron groups. So that's a tetrahedral electronic structure. And in this case, we've got 4 identical atoms around it, so it's a tetrahedral molecular structure too. So we'll draw that. Let's draw the carbon, the hydrogen, this hydrogen. These are all in the plane of the paper. And then we have a wedge here with this hydrogen. A lot of people color it in. And then we have the dashed wedge going back. So that's our tetrahedral shape for methane. And we go back to the previous picture. It's this one here that we're trying to show, but I don't like how far apart that wedge is. That wedge is like too far up there. So I think the book is sloppy on this case. This wedge should be, closer and should be like that. So I would take off for that if I was grading the book. Okay, so there it is. That's methane. Now, notice methane and methanol have the same beginning part. And that's, again, it's this CH, and the carbon's bonded to 4 things. So we've taken an H off and put an OH on. So we put a hydroxy group on there. So you should have in your brain this idea of a single carbon thing. If a single carbon, it's got 4 bonds to it, and it's in this shape here, and we could just put different things on all 4 pieces. So let's just draw the same shape here and put an OH on top. It doesn't really matter where you put it, but let's do this. I'll draw my little lone pairs. And so that's methanol. Let's figure out the angles since we're here. And we've got that page on the previous page. So what are all these angles here? Yeah, 109. I think some get real precise and say 109.5 degrees. And it's all of these angles. There's a bunch of angles here. There's like 5 different angles. And for a tetrahedron, they're all the same. So we have all those same angles down here. What about the water one? This one right here. How many electron groups do we have? Well, we got these 2 lone pairs. And so we got 4 electron groups around that oxygen. So it's also 109. So around the carbon here, the electronic structure is tetrahedral electronic structure. Around the oxygen, 4 electron groups, also tetrahedral electronic structure. Okay, but this really is just, this piece of the molecule is just bent. Doesn't have 4 atoms around it, but it's a tetrahedral electronic structure. So the electronics cloud is that way, and then we have different things stuck on the ends. Okay. Yes. Oh yeah, very good. Thought something was on the board.
So does that mean the whole thing has 8 electron groups, like the total?
Yeah, but we will. That's a good point. We have all of these different electron groups, but whenever we're dealing with the electronic structure, we're at this point in your education in chemistry, we're just sitting on a particular atom and counting them around that atom only. So we would count on the carbon. We'd sit there and see 4. And so we know the structure around that carbon is tetrahedral. And then we would sit on the oxygen and count them up. And there's 4 around that. So it'd be tetrahedral around that oxygen. So we go from every atom and look around, and we use this table here to sort of pick a different atom and see what's around it, and then pick another atom and see what's around it. And so in this larger molecule, we can go atom to atom and see how the electrons are around that atom. Okay, let's build a bigger molecule, propane. So we got 3 carbon atoms, and we've got 3, CH3. So this is the CH3 piece right here. You see right there. That's a methyl group. And then this piece in the middle, the methylene, is right here. And then this last CH3 piece is this one right here. So you see how that line, we call that a line structure formula. When we're writing out in a word processor, a text file, we can just say CH3, CH2, 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 CH3, and we're just building the molecule, and that allows somebody that's reading that to know the structure of the molecule. It's a lot more information in this I call it a line structure formula. The molecular formula is equal to C3H8. And there's not a lot of information there, is there? Right. So this is way better in terms of the line structure formula because we don't have to write out the Lewis dot structure. We can just write out CH3, CH2, and so on. Okay. Now let's make this three-dimensional. So this is all flat, and we don't, those electron groups want to get away from each other. Every one of those carbons has what kind of electronic symmetry around it, or electronic structure? What's that? Tetrahedral. Yeah, tetrahedral. Every carbon has 4 groups of electrons around it, and so it's tetrahedral. So we're going to go ahead and draw, let's do a carbon like this, and we'll go up and draw another carbon, and we'll go down. They do this zigzaggy pattern, and that's going to be, again, 109.5 degrees. And so let's draw this angle for one of the hydrogens. Draw the wedge here and the dash, and draw 2 H's. And then on this methylene, we have a wedge on top, and an H, and a dash on top, and an H. So there's the CH2. And then this one, we have a wedge, and an H, and a dash, and an H. And then we have this hydrogen is in the plane of the paper. And so in the plane of the paper, we have all of these 109.5 degree angles. And you can kind of see how this is what propane would look like. But if we did butane, which has 4 carbons, we would just add another piece on where that hydrogen is. And then pentane, we would add another carbon, hexane, octane, dodecane. If there's these long chain hydrocarbons, just get longer and longer and longer. And that's what you've got. All of those carbons are tetrahedral. Now you can imagine this gets pretty tedious. And so organic chemists, when you get to organic, you draw it like this. And that's it. That's propane in organic chemistry.
I love it.
It's way easier. Just draw where the carbons go and don't even write C. Okay? It's just a line like that. So you've got a little key here, the little caret symbol on top of 6, that's propane. It's a little angle. That's organic chemistry. Okay, so let's draw one now. Acetone, it has a carbonyl. So we the last time we looked at those different groups, we had this R, C double bonded to O, R, this carbonyl. That's this CO piece. And so in this case, that CO has got a methyl on one side and a methyl on the other side. So we would draw it like this. If we were going to draw a flat Lewis dot structure, this is what we would draw. This is the first CH3. Then we have a CO. And then we have another CH3. And if we were to add up all of the electrons, we would have 6 left over, and we put those on the oxygen. But notice this carbon doesn't have an octet, and so it's going to form a double bond, and it's going to have 2 lone pairs on that oxygen. So that adds up to all of our valence electrons, and that's acetone. How many people have know what acetone is used for? What?
I use it to take my nail polish.
Yeah, so nail polish remover is acetone. So all of the nail polish polymers that they use, they mix coloring in with polymers, and then you paint that polymer on, and it's a polymer that dissolves in acetone. Okay. Now acetone is it'll dissolve the fat out of your skin a little bit. It'll dry out your skin. So if you use too much of it, your fingertips will crack and get dry. And some people were concerned about the toxicity of acetone, so they start making acetone-free fingernail polish removal, and all it is they just add another carbon right here. It's methyl ethyl ketone instead of acetone, and so they just add one more little methyl group, and it's a slightly less toxic for your body. So I don't know what makes it toxic or less toxic. Yes. Pardon? I'm not clear on, because it's still used. Like if it was acutely toxic, like if you got it on you and it made you sick, they would get rid of it. So this is one principle you can take to the bank, and that is the toxin is the dose. And so if you're soaking in it all the time, it's going to hurt you, right? So use it sparingly. Don't soak your hands in acetone. If you spill it on you, wash it off. If you're washing an organic or tarry substance, this is kind of off the topic of the course, but this is my area of research, is cleaning things. And you want to get an oil or grease off your hands or whatever, do not put water on it first. Put the soap on first. Okay, so you soak that soap in and mix it in with the straight soap with the greasy or oily thing, and then use water. The soap grabs hold and makes a bridge between the oil and the water. So you want to get the tails of the soap into the tarry substance, and then let water pull it apart. And so it'll pull all that stuff out. Anyway, that's a pro tip. Okay, so we're going to make the 3D shape out of this molecule. And we have now two different types of atoms. These carbons here have 4 domains. But this one right here is trigonal planar. It's got 3 domains. So let's draw that one in the middle. So we have this carbon in the plane of the paper, the oxygen. Another carbon here, another carbon here. So this is 120 degrees. This is 120, and that's 120. Because this carbon here is trigonal planar electronic structure. Now let's put the methyl groups on there. Let's draw one of those hydrogens in the plane and the other hydrogen in the plane. And then we'll use wedges and dashes to draw the other 4. So that's acetone, and that's as best you can do for 3D, the 3D structure of that molecule, if you're just drawing on a flat surface. So these 2 wedges, those are hydrogens coming out of the board and dangling down. And then the dashes are hydrogens going back into the board, angling down. So those 2 are looking like this, like little scissors sticking down. Same here and here. But everything else, if you're drawing a straight line, those are indicating that that's in the plane of the paper, or the plane of the board. So that's acetone. Organic chemist would write this. And then just draw the double bond, and they would write the oxygen. And a lot of times they leave off the lone pairs. Lazy people. Okay. But that's what we would draw for acetone. Okay, let's have some fun now. Rubbing alcohol. We've done acetone. Let's do rubbing alcohol. So 2-propanol. So this 2, we see this OL. We know that's an alcohol. So isopropyl alcohol, this OL, is indicating that this is an alcohol. The proper name is 2-propanol. Prop means 3 carbon atoms. 3 carbons. OL means alcohol. The 2 tells us what carbon atom it's stuck to. So let's do the CH3. Everything has 4 electron domains around it, including the oxygens. So everything's going to be 109.5 degrees. Let's draw the backbone. We have the carbon, 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 and hydrogen. There's our propane. And then now the OH is going to be on a wedge or a dash, and we have a choice to make. What do you want to put it on? The OH, or you want to put it on the wedge or the dash? The wedge. Okay. So we have OH, and then we have an H on the dash. I mean, yeah, that's right. So everything has 4 electron domains around it. Everything's 109.5 in this molecule. So even the oxygen, the OH, COH angle. So that's another way to write these things too. So if I wanted to ask you a question, I might say the angle for COH is equal to, right? You see the COH, we're looking at the angle of those 3 atoms, and so that would be 109.5. But that would be a way I might ask that question. And then here's the CCC angle. So this one right here would be the angle CCC, 109.5 degrees. And then these right here would be the angle HCH. Now, organic chemists would write this as they would draw propane, and they would draw the wedge like this and put the OH on there, and they would just write OH. But they leave all the hydrogens off. So the implication is if the OH is coming out of the plane and is in front, then the hydrogen's in the back, and they just omit it. So that's how an organic chemist would write 2-propanol, would draw that dash. I mean, the wedge coming out. Okay, let's do propene. Now, this is a little different. We see one little letter different. And so that means there's a double bond in there somewhere. So notice we've got fewer hydrogens. We used to have CH3, CH2 for propane. Now we've lost 2 hydrogens. So we're going to be making a double bond. So this one is going to be let's draw just as if it's a regular backbone. We'll draw this methyl group on the right, CH3, we know that. This has H2 and an H here. So there's all the atoms. If I were to add up the valence electrons, I've got 2 more. I've got 2 left. And I've got 2 choices to put them on here. All of these carbons only have 6 electrons, both of these actually. And so if I put them on this one, it's going to share with that one. If I put them on that one, it's going to share with this one. So they're just going to make a double bond. And so that adds up to all the valence electrons in this molecule. I know it's a double bond also by naming convention. So organic chemistry would tell you that E and E is a double bond. A and E is all single bonds. So propane is all single bonds. Propene has 1 double bond in it. So let's draw this in terms of our electron domains, because these 2 right here are going to be trigonal planar. So I draw the methyl group over here with the wedge and the dash methyls, but everything else around these carbons is planar. So I have CH2 bonded to CH, and so these are all 120 degrees. And then this one over here, this angle, is 109.5. So that's a really good molecule to test you guys with, because you got this 3 domains around this carbon, and so 120 degrees around any of those. This carbon here has 3 electron domains, so 120 degrees around that one in all directions. And then this one has 4 electron domains, so it's tetrahedral electronic structure, so it's 109.5. So that's pretty simple. And then this molecule, organic chemists would just do this, and that would be propene.
So the angle of like CCC would be 120.
Yes. So CCC would be 120. Mm-hmm. And it's just based on that central carbon. Good. Okay, so let's do something different. Wake you guys up. All right, so we've got now an Alex prediction of whether these molecules will be polar or nonpolar. And so here we have OCS. So what we're really looking at is just, you've got, if they're different atoms, okay, the oxygen is more electronegative, and so it's going to be partially negative, and the sulfur is down from that. It's going to be partially positive. So there's going to be a dipole moment on this, okay? And so this is going to be a polar molecule. And the atom closest to the negative side would be oxygen. So you just got to go through and look to see, if it's going to have a dipole moment over the whole molecule. Now, what we just did is important for the next one. See, it says CH3Cl. So that's going to be CH3. We know that's a methyl group. And then that Cl with its extra electrons. And so chlorine, way over there, it's going to be electronegative. It's going to pull all those electrons here. So this top part of the molecule is going to be negative. The bottom part of the molecule is going to be positive. So it's going to have a dipole moment that points up towards the chlorine. And so the chlorine is going to be the one that's closest to the negative end of the molecule, and it's going to be polar. Now, I2, you got 2 iodine atoms. So is that going to be polar or nonpolar? Nonpolar, because they're the same atom. There's no reason why electrons would spend more time on one iodine versus the other. So I2, again, neither side of that molecule is more negative than the other. So that's going to be nonpolar. And so then there's no answer for the second column. Okay, let's do some more. Okay, CS2. So here we have an S on one side. It's very similar to CO2. If you look up at the periodic table, notice where S is, it's right below oxygen. And so CO2 has a double bond between the carbons and the oxygens. If we just swap out the O's with S's, we have the same structure. And both ends of the molecule have sulfur on them. So these individual bonds may be polar, but look at the angle they're at. They cancel out. And so even though this has a polar bond, they're opposite directions. And so there's no one side of the molecule is positive and the other side is not negative. It's the same on both ends. And so even though the individual bonds are polar, the molecule is nonpolar. So we're determining whether the molecule is polar, not the bonds. Okay, what about this carbon tetrachloride? Cl. The Cl are so much more comfortable with these pictures now that you've seen them a whole bunch. And here's carbon tetrachloride. We could put all of the electrons on them if we want. I like this tablet, it's pretty sensitive. Okay, so there's all of our carbons and all of our chlorines, and each individual bond is polar. They're pointing out towards the chlorine, but one side of the molecule doesn't have any more negative, character than the other. All of these little dipoles on the bonds are kind of like 4 bungee cords, and they're all canceling each other out. So this molecule is nonpolar because it's so symmetric. So we would mark that one as nonpolar. And then ClF, I mean, again, you've got chlorine on one end, fluorine on the other. Fluorine's more electronegative than chlorine, so this side will be negative, this side will be positive. So it would be F on this end, and it would be polar. If you're in a situation like this where you've got all of the same atoms all the way around in all the bonding positions, just assume that that molecule is nonpolar because all of the angles are canceling each other out. Okay, let's look at the pictures though of these charges. So these are electrostatic potential maps. So it's as if we walk along the this is the way that's described to me, that when the computational chemistry package does it, it calculates the shape of the electron cloud. Okay, so where it's fatter, you have more electrons, and so that would be a bigger atom. Where it's smaller, that's a smaller atom because it's the size of the electron cloud. And remember, hydrogen was 4 counties in Texas, and sodium was the whole size of Texas. So further down the periodic table is the bigger atoms. And then if we walk along that surface with a positive charge, it's either going to be pulled down toward a negative part of the molecule, or it's going to be pushed away by a positive part of the molecule. So we can walk around with a positive charge in our hand and determine what the charge is on the electron cloud as we walk around. So the whole molecule might be neutral, but there might be a negative part of the molecule and a positive part of the molecule. And that's what we call a dipole moment, and that's what we're looking at here. We color the negative charge areas red and the positive charge areas blue. So this side of the molecule is negative, that side of the molecule is positive. So with that picture and those ideas in mind, we need to look here and see what's the possible molecule that would give us that shape. Okay. And so we've got 3 atoms, so that's good. This is the only one that doesn't have 3 atoms, and so we're going to mark through that. It can't be HF because there's 3 atoms. It doesn't look like it's going to be CO2. Why? It'd be the same on either side. And see, right here, this CO2, it would be the same on both sides, and it's not. So it's not that one. Here's SF2, also not that one because it's not the same on both sides. So ClCN, okay, so we might have, again, as we go to the right, those atoms get smaller and smaller and more negative. And so this could be the Cl, C, and N. So that's possible. So we might color that one in as a possible chemical formula. And then HCN. It's probably not this one because this, how would we write that? Well, the more negative atom would be the nitrogen. So we might have the nitrogen here and the carbon in the middle and the H here. But this is too big for an H. And so it's probably not this one because that positive atom is just too big. It's bigger than the carbon, and we know hydrogen's really tiny. So that would be the answer for this one. This one requires a lot more thinking because you're looking at the sizes of the atoms and you're looking at their negative electronegativities on the periodic table. So let's do some more. Okay, here's a bent molecule. 3 atoms. Do you see that there's 3 atoms? So it's not going to be this one, C2H2. HCN, that's going to be linear. And so it's not going to be that molecule. This one has got 4 atoms, so it's not that one. So I guess it could be SO2 and NO2. Does it make sense though that these are going to be negative on this end? Are the oxygens going to be more negative? Yeah, more negative than the sulfur and more negative than the nitrogen. So it could be either one of those. And again, these are all, check all that apply. So it could be either NO2 or SO2. All right, what about this one? Which ones can I eliminate? What's that?
Carbon dioxide.
CO2? That, you said that fast. Why?
There's 3. But
Yeah.
There's only 2.
The 3 atoms here, only 2 in the picture. Okay, so we're going to scratch that one out.
H2.
Okay. H2, why do you say that?
Because the picture's not symmetrical.
Yeah, so there'd be the same shading if it's 2 identical atoms. So we would scratch that one out too. Okay. We have 3 more possibilities. What are you thinking?
Probably HCl because that's too big for hydrogen.
Scratch out HCl.
Scratch it out.
Because the positive end of the molecule would be the H, right?
Yeah.
And so for HCl, this would be the H and that'd be the Cl. The Cl is negative, but this is too big for a hydrogen. So we would scratch that out. Same for HI too, right? Yeah. And so does this make sense for IF? So F would be much smaller than I, and F would be more negative than I. So the smaller atom's more negative, and that fits the picture. The smaller atom's more negative, so that would be IF. I kind of like these pictures because it makes you think in terms of the reactivity of the molecule. You know, if this molecule comes in and wants to attack another molecule, the red side is going to attack a blue. It's going to go after the negative piece of this molecule is going to attack a positive piece on another molecule. And that's what's going on when we have the chemical reactions. All right, let's draw a few more small molecules and then we can call it a day. So this goes back to the resonance structures. This one's not in your notes, so I just wanted to add some more to draw. So we have C6H6. Now this is kind of a strange molecule. If we were to just draw it, let's try to draw it wrong first. There's my 6 carbons, and I've got 6 hydrogens. Well, let's see. I guess I could draw. Yeah, there's a way to write this. Okay, this is one way to draw it. Here's my 2 methyl groups to get rid of the 6 hydrogens. And if I added up my electrons, I've got 6 times 4 is 24, plus another 6 is equal to 30. So how many have I used? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Did I count that right? Okay, so I have 8 left over. So I can form 4 more bonds, like making double bonds, triple bonds, and so on. So let's 1, 2, 3, 4. So that's one way to write C6H6, but that's not benzene, but that is one way to write it. It's be kind of like a polyacetylene, but benzene is actually a molecule like this. It's a planar molecule, so it's easy for us to draw. It's a fantastic molecule. So if we count up all of those bonds, we have 2, 4, 6, 8, 10, 12 for the carbon-carbon bonds, okay, and another 12 for the carbon-hydrogen bonds. So we had 30 electrons and minus 24. Okay, so I've got 6 left. And so I can make 3 double bonds. Now, I have some choices if I'm going to make 3 double bonds. You know, these carbons all have 3 domains. They want one more bond each. So I could put a double bond there. Now those 2 carbons have octets. Okay, so I wouldn't put a double bond here because this carbon already has 4 bonds. So I put a double bond there. Now these 2 carbons have octets. And so then this last bond, double bond, goes there. And so that's using up my last 6. So I'm used up all my electrons. So there's my benzene molecule. But remember, I had a choice. What if I had put the double bond over here? Well, that's the resonance structure that we have. I could have put my double bond to that carbon. So this is benzene and the 2 resonance structures. You see the only difference between the resonance structures are the locations of the double bonds. Okay. And that also kind of causes an averaging out of the bond lengths. If you look at this molecule the way it's drawn, how many bond lengths of how many carbon-carbon bond lengths would I have? How many different types of carbon-carbon bonding do I have? Yeah, it looks like 2, doesn't it? I've got carbon double bonded to carbon, and I've got carbon single bond to carbon. So I would have 2 different types of bond lengths. When we take this molecule to experiment, we see 6 identical bond lengths. So we don't have the left picture or the right picture in a pure form. So it's sort of the average between the 2. And so we call this averaging, this resonance is giving us these average bond lengths, and we see experimental evidence for that. So we don't have what we call cyclohexatriene, so 3 double bonds, cyclohexane or cyclohexatriene. We have benzene, and an organic chemist would write it like this. They would just draw this little hexagon. Now some of them will go ahead and draw the double bonds like that, and they'll just assume that you could have drawn them the other way. Okay, they could draw them in resonance if they were, being particular. So when you get to the organic, this is how you're going to see benzene. We're going to just delete all the hydrogens. Now, if we delete all the hydrogens, how do we know how many hydrogens are on here? How do we know there's not a CH2 right there? What tells us that that's not a CH2, but just a CH?
And then we wouldn't have a wedge.
Well, I mean, I could draw a wedge in the dash, but that would make carbon have 5 bonds. And so we know carbon bonds, there's only 4 lines that go to any carbon. Even up in here, this crazy molecule I drew up here, that carbon has 4 lines drawn to it, 4 bonds, 2 sigma bonds and 2 pi bonds, which we'll get to in the next set of videos. This carbon has 4 bonds. It has an octet, right? And so we can look down here and we see this carbon only has 3 things bonded to it. And so the 4th thing has to be a hydrogen. So you see how much organic chemists are leaving out. So it's a big jump when you go from here. Now, you've still got Chem 2 ahead of you. That's where you get into equilibrium and some other stuff. This is kind of a foreshadowing. If you go on to organic, it's a big jump. You get into organic, you start seeing these things, and you're like, what happened? Where are my hydrogens? Okay, so I'm just trying to lay a little bit of a ramp to that next course if you have to take it. Okay, and then if you don't have to take it, you'll still see structures like this on Wikipedia. So here's glucose. Okay, and you can look up here at this molecule of glucose, and now, after today, you can understand, like real world, you go out there, you type in glucose, you see that structure over there, and you can figure out that, hey, those lazy organic chemists are leaving off a lot of hydrogens. Okay, but at least you understand, and you can understand the wedges and the dashes too. So this is, all the carbons, C6, H12, O6. We can count up the oxygens and the carbons, and then you get half the hydrogens. The other hydrogens are just omitted. Okay, so let's draw this ourselves. And this is OH, carbon. We have a wedge OH, dashed hydrogen. We have a wedged hydrogen and a dashed hydrogen. Carbon. Here we have a dashed OH, so we have a wedge hydrogen. This crazy carbonyl stuck out here. And then H. So we've got all kinds of bond angles. Let's see, what's this angle right here? 120, excellent, 120. And let's pick one over here. What is this angle right here? 109.5, good. So that's glucose, C6H12O6. But you look at this molecule, you don't see H12, do you? Because we've omitted the H's right here. We had an H's right there. We had an H right here, an H, an H, an H. Okay. So we've left off 6 of the hydrogens. Because once we have those carbons and we know what 3 of the things are, the other 4th one is a hydrogen. Now, in order to keep track of these different patterns of the wedges and dashes, and also this molecule can turn into a cyclic molecule. These electrons here can go around and hit the molecule right there, make a ring structure. Okay, and this is some of the hydrogens OHs go down, other OHs go up. And that pattern of the OHs going down and up and so on is really important for our body and the way we can utilize these different kinds of sugars. Sugars, starches, and cellulose are the same base structure, okay? And whether the OHs are on the right or the left can change this molecule from a sugar, one that you can use for energy, to something that you can't use for energy, like a cellulosic material or fiber. And so a lot of the fiber that we eat just really is there to keep our guts clean, that we don't digest it, and so it helps us keep our gut clean. But if you were to change some of those OHs and how they are a wedge or a dash, then it becomes a sugar, and the enzymes in our body can latch onto it and make energy. So the structure of these molecules is really important, and you guys are learning the foundation of that. The Lewis dot structures first, then this VSEPR gives us the 3D shape. And that's where the wedges and dashes come. And I think that's it. All right, so you guys went through a lot of structures today, so hopefully that helps.